And with that, I'd like to bring to the stage Professor Alberto Sangiovanni-Vincentelli.
First of all, thank you very much for inviting me, and I cannot be happier than being today with you also because of all the people who like what I do. I guess National Instruments is by far the best. So they actually took the concept of platform and platform-based design to an industry. And so being a university professor but liking what happens in industry, I cannot be more pleased than this. So let me give you some insight about cyber-physical systems, how to design them, what is the trend in there, and give you some perspective on what we see coming in the next 10 to 20 years. Okay. So the title of my talk is provocative. In some sense, what the end of this cyber-physical system is actually designing very hybrid systems, for example, Frankenstein monsters. So we'll see that it's actually possible to do so if we use platform-based design, of course. So the outline of my talk is about cyber-physical systems. So I will give you some insight of what are the technical challenges and how the term came about. Being, again, a university professor, I like to define things, and cyber-physical systems is one of these terms that have many meanings to different people. So I'd like to give you my own meaning and the history of it. We'll look at design methodologies that are being used for this kind of systems. And then I will start looking into the crystal ball. So we'll look at the swarm at the edge of the cloud and then the outlook of what we can do in this new world. So first thing is talk about cyber-physical systems. So we heard Dr. T explaining what cyber-physical is all about, especially in the application domains. And this is a snapshot of what cyber-physical system could be seen. But in my opinion, the abstraction of what cyber-physical system is about orchestrating network computational resources together with physical systems. So it's a connection between computing elements, communication elements, intelligence intended as digital signal processing and the like, and the physical world where we take measurements and we come back and impact this physical world. Now, a little bit of history. Actually, cyber-physical system, the name was born about 15 years ago in Berkeley, and was a discussion with my colleagues there. And we said, well, gee, you know, embedded system is passé, so nobody wants to fund embedded system anymore in National Science Foundation, DARPA, and so on. So we have to invent a new name. So cyber-physical system sounds just right. And so guess what? Boom, another wave of big financing. But the origin was exactly the same, right? This embedded system is to put logical objects inside physical systems. Okay. Once we invented the name and we got the money machine running, then we had to put content into it. And it was slightly different than what we were used to do before. And so scratch, 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 it came out something like this. So is, again, orchestrating network computational resources. So what we did is that we extended the field of embedded system to consider highly distributed systems. And the fact that highly distributed system needs an orchestration, because the other key difference is that this widely distributed system have to perform one particular task. And so they have to corral their resources to yield something that people want to use. Now, the other aspect is that if you think about these large systems, the physical part of the system is multi-physics, in the sense it's not only an electrical system, but it's also a mechanical system. It may be a chemical system, it may be processing machines and all of that. So it's heterogeneity. So it is distribution and heterogeneity. So these are the kind of new way. But also from the design point of view, if you look at what we used to do in automotive, for example, which I worked since 1988, AutoSAR was one of the outcome of platform-based design thinking. The idea was you have a physical system and you put a controller into it to make it work better. Now, the other idea that we brought in new with respect to embed the system was you have to design together. So not only the mechanical system and then you put the electronics on it, design it together so that you get much better efficiency. So again, computation and networking integrated with physical processes. So the problem then is to manage dynamics. Another thing that we didn't do in the past was to design for dynamics. Most of the things that we know how to do are in steady state. We used to be able to do. Now we put emphasis on the dynamic behavior, on transients, on trajectories, on things of that sort. So this is the, how to say, the intellectual core of what a cyber-physical system are all about. So in fact, if we take an example of companies that are really in the middle of the cyber-physical system domain, I would like to use UTC, United Technology Corporation, as a good example. Now, UTC in the old times was actually one of the largest companies in the world because it had Boeing, United Airlines, Pratt & Whitney, and so on. So at some point, the government said, okay, this is a bit too much. So they cut away the part about Boeing and United Airways, so they separated that. What is left is still a humongous conglomerate of companies, and they do things as different from climate control all the way to helicopters. Sikorsky is a part of it, and Pratt & Whitney, and Hamilton Sandstrom, and even Otis elevators. So that's all UTC. So this is heterogeneous, all right. It's cyber-physical system, all right. And so it's very interesting to see how this company is managing these kind of challenges. So the key point that they have to face is more integration. So they have to integrate more the various pieces of their designs. For example, Sikorsky, being a helicopter, has a lot of components. There's a lot of very challenging mechanical problems to get the helicopters running. On top of it, there is a lot of control that goes in, plus the connection to the weapon system and all kind of other things. There is also the issue of managing things as mundane as supermarkets and make them be much more energy efficient and save with respect to things that get thrown away because they're, how to say, they are spoiling, so you don't want that to happen. So their challenge, as the CEO of UTC posted, is that they have higher functionality, which are demanded from products and systems, and they have, of course, as everybody in this room, I guess, have much more pressure on speed of development and deployment, bringing it to be deployed in the field, with much more software content. And software is a way of customizing a solution, which is a generic solution, to the need of a particular application. A much more complex system interaction. So the way in which you design a helicopter today is totally different from what you used to design 10 years ago, because the sideways interaction between subsystems is becoming so crucial that if you don't master the interaction between subsystems, you very likely are going to design things that crash. Now, the 787 is, Boeing 787 is a clear example of how complicated things are becoming and how difficult it is to manage unwanted interaction between subsystems. So what we said is that we use tools to architect, design, and test that are already proven inadequate in the sense they are not powerful enough. So there is a big need of work in that domain, and I'm very glad the National is indeed bringing these things to bear. And hear me, there is very important point that we all care about, and especially me being in academia, is the fact that people are trying to bring much more complex products to the market with insufficient talent pool. There are not enough engineers which are trained in the system thinking. And system thinking is not what we used to teach students in class. We tend to teach particulars, electronics, mechanical, civil, and so on. So the new trend is to build an engineer who can master the collaboration and integration of all these different fields. And this is very rare. So these companies are really asking, begging the academic world or whoever can teach this kind of stuff to bring more people to the market. So we say cyber-physical system is a tale of integration. So why it is a tale of integration? We cannot rely upon people that know very well only one field. And so this is a classical example of the elephant, and many people running around and trying to figure out what an elephant is from its components. And so you say it's a rope, it's a tree, it's a snake, it's a spear, it's a fan, and of course none of this is true. It is an elephant, because being an elephant is the integration of all these different parts that people see. Now, if you look at this one is actually a very simple model of what you have in airplanes is the secondary power generation system, is what powers, for example, the entertainment system, the air conditioning system, and so on of your airplane. And in here you have these generators that are connected to loads by contactors. There are two independent systems, and you want them to be always, at least one always active, otherwise plain boom, right? So the point is that how do you master the connection between loads and generators such a way that the important loads are always connected? Now, if we look at the diagram of this system, you got an electromechanical system, the generator, the contactor, which is this big switch. I mean, when we talk about big, is big, right? So there's a lot of dynamics in there. Is a mechanical system. Then you have buses that carry electrical power. So that is an electrical system. Then you got a supervisor, finite state machine that controls all the closing and opening of the contactors. And then you say, well, it is a software system, and so on. So what you see is, again, the elephant syndrome. So in the past, we used to have different engineers taking care of all these parts, and then miracle happens, you put all of them together, and it works. Not any longer. So we have to change the way in which we design these things. So the issues are about, and I bet that anyone here who is in systems, automotive systems, or airplanes, and so on, the issues are about faulty design, long redesign cycles, because you find an error and you have to redesign all over again, missed customer expectation. For example, the 787 is about 5 years late. Is supply chain management. For the 787, there is a supply chain which is extremely long and extremely complex, many different companies coming together, testing. And of course, here we are very happy to hear the word testing. Multitude of domains, we said before. The computing platform themselves are becoming heterogeneous, meaning that you have tons of design of digital signal processor, tons of processor, ton of cores inside the processor. So it's a very complex platform to carry on the control computation. There are severe integration difficulties, and in fact, most of the bugs, very serious bugs, are discovered at deployment time. Because only when you deploy the system, you see the interaction between subsystems, if you don't change the way in which you design. And then finally, we say engineering skills. So there is, in my view, one way that will solve some of the problem is to bring formality and rigor. Always formality and rigor make a big difference when it comes to design. So if we look at the VLSI domain, where I grew up and where we've discovered many different ways of doing synthesis, for example, logic synthesis, layout synthesis, and so on, this has become possible because we have a mathematical formulation of the problem we are trying to solve, which is robust. And so it is amenable to abstract algorithms and tools that implement the algorithms that we are talking about. Okay, so we come to the design methodology issue. So many of you, especially in Germany, hello? Okay, are used to the V design process. Why is that? Because the V design process was actually originated in Germany about 200 years ago in the military systems. Okay, and interestingly enough, the V model, the V diagram, is now considered to be the way to go for all systems. In my opinion, it was good 200 years ago, it's terrible today. Why it is terrible today? Because it's a waterfall model. So you do one thing, then you do another, then you do another, then you do another, then you put it together, then you put it together. Oh my God, it's all wrong. Come back and start again, right? Tutum, tutum, tutum. And guess what? Faulty design, long redesign cycle, and all of that. So please, even if you are in Germany, don't do this anymore. Just get rid of it, okay? It doesn't scale. Okay, so here it comes, the platform, right? And so that's what I came up with about, I would say 18 years ago, when I was working in the automotive domain. So I was trying to solve a problem in Formula One cars when Magneti Marelli designed the first example of a semi-automatic gear switch for Formula One racing, 1988. So remember, in 1988, we had 8-bit microcontrollers, right? So we're talking about big computational systems. And the great computer language that we used to design the controllers was assembly language, okay? So we are trying to implement algorithms in assembly language, and that was a challenge, right? So I said, there must be a better way of doing things, and I came up with this kind of view that the design problem is always a combination of two things. Is a bottom-up part, which is using what you already have available, in this case, the 8-bit microcontrollers, assembly language, and all that. On the other side is what you want to accomplish. So this is what you have, and this is what you want to accomplish. So it's a meet in the middle. There is a top-down part, which is what I want to do, and there is a bottom-up part, what I have, and how I can use what I have to solve my problem. So here the origin of a platform, right, and platform-based design, is that try to use as much as possible what you got, but in order to do so, you have to be able to play with the components as Lego blocks, right? So you have to be able to plug and play. Now, I used to say that plug and play, especially in the Microsoft era, remember plug and play came with the first version of the Microsoft operating system. It was more like plug and pray, right? And so rigor and formality comes to the rescue in sense of making plug and play a reality. So when you think about platform thinking, and when Dr. T was saying, oh, we have all these wonderful platforms, see here, the bottom line is that it's more or less the same object, but is used in many different ways, right? So in order to be able to do that, you have to have very rigorously defined interfaces so that you can put together all these components. Now, the key issue then is to find the way of the glue, right? The glue is becoming more important than the actual components that you're gluing together. Is the glue, is a combination of things. Now, the interesting thing is that this view of bottom-up, top-down is actually can be applied to any field in the world. And the fact that you have to focus on the glue, on putting together the component you have, doesn't matter what you do, it's still valid, okay? And this is a kind of an eye-opener when we applied this thing to synthetic biology. So people in synthetic biology, they are trying to design bacteria that don't exist in life. So they are artificial bacteria, but they are living organisms. They use exactly the same principle. Okay? So it's kind of interesting that coming from automotive, we go to synthetic biology. But because it's a very simple concept in some sense, but it changes the way in which you think about design, or at least I think so. Okay, now, take that model and twist it around, and this one is, instead of an hourglass, is the bow tie model, which is essentially the same thing, except it is an interesting way of looking at the separation between the functional space and the architectural space. One thing that I noticed when I was trying to solve the verification of the semi-automatic gear switching way back in '88 was the fact that the implementation and the algorithm were one and the same. When I went and asked the engineers of Magneti Marelli, please give me the algorithm that you use to control the gears, they said, it's here. I say, what do you mean it's here? What is the mathematics of it? And they gave me a nice listing on an assembly language program, right? So they say, this is not the algorithm. This is the implementation of the algorithm, right? So please keep them separate, because I cannot verify if your algorithm is correct by looking at assembly code. That's a wrong level of abstraction. You already put in too much information with respect of what is needed to verify if the algorithm is correct. So guess what? I had to go through every single damn line of assembly code and build a finite state machine that, in my opinion, was doing the same thing. So it's reverse engineering, right? And lo and behold, we did find the problem, but was a corner case of a finite state machine. Now, to find that corner case in the embedded code, right, in the assembly code, it would have taken about 1 year, okay? And it take us, what, 5 minutes, maybe, to discover that was a corner case of the algorithm that was not working. So please also always keep in mind that one thing is what you want to do, and one thing is how you're going to do it. And this is one of the big faults of the V model, is that when you verify, you already verify the implementation. It's too late. Verify the algorithm, verify the code, verify the implementation. Okay? Early. Bring up the verification as early as you can so that you can debug as early as you can, and you can come to market much faster. Now, there are a lot of people that say, oh, yeah, great, so you want to use only existing parts. Never say that. What I said is that you have to think that way. Now, if you want to design a component, a system in which no existing part can help you in one side of your design, then my intellectual framework allows you to put a placeholder. It's as if you had the component, but you don't have it. You just postulate its existence. And so when this component comes to be important in your design, you're actually designing it, but now with precise requirements. And the requirements come from the top-down part of the thing. Now, what does this do to you? The point is that now you have very precise requirements. This is a very good point in any system design. You have to have requirements. And requirements have to be as precise and as mathematically expressed as you possibly can. Now, that's one good thing. The second good thing is that if you think about the fact that this component may enrich your library later on, you design it having in mind where else you can use this thing. So the requirements not only become the requirements for that product, but they become the requirements for a family of products. And so you have embedded in the way in which you design the components the idea that you are going to redesign with that component. Now, since people are really attached to their idea, I had to give a rendition of what platform-based design may mean to a V fanatic. And so the V fanatic will see platform-based design as being a local V. So also in General Motors, they used to call this methodology that I try to import into their domain as small v in big V. Okay, right. I love to think about platform, but if people like to think V is small v's in big V's, right? And the small v is that kind of thing that I was talking about doing designs and verification at every layer of abstraction. So now this is what it is today. So that's the situation, cyber-physical system, and what you want to do with that, and the use of platform, why platform came about, and this idea that platform is not only the idea of using a common node in which you can solve a myriad of applications with the same components, maybe assembled in a different way, but it's the same domain of components that serve many applications. But there is also an interesting point to think about the future. So where are we going in terms of an embedded system or cyber-physical system? Is the emerging IT scene, information technology scene, which is after all our platform, a mega platform, okay, if you like. So here comes age 1960s, right? So when I started my university studies was 1966. So what we got these horrible monsters, right? So we were less than 1 megabit, less than 1 megabyte of memory, less of anything, right? And we went by with punch card, okay? And so did you have terminals? The only terminals you had is a machine that you used to punch the cards, right? Now then, later on, we started having some terminals, and they were alphanumeric terminals. And now, fast forward 40 years, and what you got? Mobile access. So the mobile access you get today. So the laptop, the iPhones of this world, and so on. So it's the way in which you access the centralized computation domain through peripherals which are smart themselves. Okay, and they are connected wirelessly, so that we are not forced to carry cables, right? Now, is that what is going to be for the next 20 years? The answer is absolutely not, at least in my opinion. And my opinion is about one thing we already saw, is the fact that centralized computing has disappeared. Now, we don't even know where computing takes place. We don't even know where our data are stored. And we have a lot of benefits from this virtualization of the core. And that's what we call the cloud. So that what you see there is the Golden Gate Bridge in the morning, right? So that's fog, right? And then you see only the peak. So that's the cloud. But more importantly is what happens at the periphery. And the periphery is the swarm, or also said the sensory swarm. So if you take the vision of Dr. T, when he said, well, I like to think about data acquisition system. This one is a planetary data acquisition system that we are talking about. So sensors are going to be spread all over the place. Let me give you some interesting numbers. So I believe that the computers and mobiles are going to disappear. Absolutely. So no more cell phones, no more laptops, except for us professionals. So in this room, probably we still use 200 years from now, you still have a laptop. But if you think about the public, right, people who are using things, and today they do use laptops and to access the internet, no longer. Because if there is going to be a Copernican revolution. So man is going to be at the center. So the interaction with the cyber-physical systems, if you like, is going to happen in the same way as we speak to each other, in the same way in which we think to interact with our neighboring world. Is going to be the same. So no need of typing. You can just talk, you can just make gesture, you can do all these kind of things, and the environment is going to react to you as a person, as a physical human being. Now, the prediction is that we are going to have 1,000 devices per person in 2020. So 1,000 devices per person. So you're not going to have 1,000 cell phones on you, right? No, not possible. But these 1,000 are not necessarily worn, are spread. So you will have rooms that are literally going to be painted with electronics. We are going to have our clothes, which are going to be full of electronic sensors for health application, as well as counterfeit applications for, designer clothes and all of that. It's going to be for signaling where you are, is for, emergency calls and all that kind of nice stuff, right? So you will be immersed into the electronic world. Okay. So there are already some companies that are taking position in this new world. And of course, being a new world which is planetary dimension, you cannot think of small companies to be capable of mastering this. So indeed, some of the people are most vocal about this kind of change, even though they don't comprehend the real implications of all what we have just said, are IBM, Cisco, Google. So these are the players, so the big guys. So the view is that you have a world that is going to be instrumented. So we said is the ability to measure, sense, and see the condition of practically everything. Is interconnected. So people and devices can interchange their ideas. By the way, this is a super Internet of Things, right? So again, what I'm trying to do is to build the concepts, right? Then all the names that we heard before, Internet of Things, machine to machine, and all of that, are special cases of this instrumented, interconnected, intelligent world, because not only interconnection, but you also want to do things, so you have to be intelligent. So you can think of application like smart water, so the managing of big utilities like water. Smart grid is a special case of this. And the interaction between all these devices is going to be so interesting. So you could use the same infrastructure to do smart traffic, smart water, smart grid. So that's platform, all right. So you're going to have this planetary instrumented system that are going to carry these applications. These are applications. Now, I told you about the health application. One of these is cyber biological system. So we talk about cyber physical system. Now we're talking about cyber biological system. Why? Funding is drying up. New funding. Not really. Now, this is more serious in the sense that it is in the interaction between the biological world, which is a special kind of physical domain, and the cyber part. So you're talking about artificial limbs, but more interestingly, and probably more importantly, is the direct connection of the brains to the environment. So it's already possible today in monkeys and in rats, not in humans anymore so far, but there's been one woman actually was connected. That was a very serious problem because she was quadriplegic, so her spine cut right here. And with this implanted chip, she could move. So because you bypass where the breakage occurs. Now, you can imagine in the future, again, I'm underlying 200 times, in the future, you may carry a chip or more chips in our head, and then have our capabilities extended so much that, for example, right now, I would really love an espresso, right? So I say, espresso, and then a robot comes down, professor, here is your espresso, okay? Wouldn't that be nice, okay? So that's, I mean, this is a joke, but if you think about how you can extend your capabilities, you can have a great painter, for example, or a great performer performing 200 miles away, a continent away, staying at his home. The swarm, we were saying. Now, why is the swarm so interesting? Why is this a Copernican revolution also in the way in which you think system is big numbers? Now, if you look at things like bees and ants and fish, their safety is in big numbers. So you have all these devices, okay, that cooperate, and the point is that they are very resilient with respect to being killed, right? So you may have a predator comes in, kills about 1,000 individuals, who cares? The swarm takes over eventually. So safety is in numbers. Now, large numbers and reliability. So humans, there is about 10% to 15% of terrestrial animal biomass. We are very intelligent beings, so 10 to the 9th neurons per node per person. And if you look at ants, it's 10 to 15, is the same kind of amount of mass. Of course, they're much smaller. But there are only 10 to the 5th neurons per node. But they have been around for about 1,000x year more than we have. So they are slightly more resilient. So easier to make ants than humans, so we have to think about small, simple, and swarm. So that's the paradigm of the cyber-physical system of the future. So, but this worm is also kind of dangerous, right? So because it's very difficult to control. I don't know how many of you have seen the movie This Worm, but more importantly, Prey, that was written by Michael Crichton. And actually, Michael Crichton wrote that movie after he came to Berkeley, saw some of the things we did, and that was about 5 or 6 years ago, in which this worm was taking over, right? So they were actually being able to replicate themselves and kill humans. Okay, so let's hope this is not going to happen, but potentially it may happen if you don't design with platform-based design, but you design with V, right? So that's going to be very bad. So now this is actually a picture that was taken of swarm of birds kind of taking down a plane. I mean, this is actually happening. It does happen. So in fact, you see in all airports, you have scarecrows and all kind of things to keep the swarms out. So you have enormous problems in terms of what may happen, but in addition to that, the security aspect. If you have 1 gazillion devices to enter into the system, it's extremely easy. So what kind of things can you do to secure this? Actually, data aggregation networking can be used to improve security by the very same mechanism as an ant's nest is a very secure place. And the way in which you do that is by finding out if you are invaded and then isolate that environment. And the key point is to realize or to measure that you are under attack. So we go back always to the same paradigm, measure, understand, activate, countermeasures, right? It's the same paradigm all over again. So there are some interesting technical work done about, you know, the capability of understanding if you're under attack and what to do about it. So, outlook. So what is in my conclusion? So the vision 2025, so not quite 2020 because, you know, Europe 2020, we're already Horizon 2020, we are sick and tired of getting this. So vision 2025, so slightly more extended. So every object will be smart. More importantly, is the ensemble is a function. So the equation, one function, one device is going to disappear. And this is the basic concept by way of the platform. And the platform puts a virtual device in your hands. And so your power is going to be enhanced and multiplied by the concept of platform because you can do anything you want. The function is determined by the availability of sensing, actuation, connectivity, computation, storage, and energy. So these are the components of the platform. Now, so if we look at the technical problem, is a humongous network, distributed, adaptive, hierarchical, hybrid control problem. So I may be able to invent a new word for this, but I'll keep it for now because now we have enough funding. So stay tuned. Final words of wisdom. So this one are two of my favorite paintings. Is about, you know, the left is the old guy who was made of books, right? It's a very serious studying man. The other one, Giorgio de Chirico, is these are called the philosophers. So it's the abstraction of what we have to think about. All right. So cyber-physical system in summary. So you have trends that are market and regulatory pressures, much more complex system level requirement. And on the challenges is that CPS, both biophysics and computational communication matter. So you need better abstractions and common semantics and co-design. So given the scaffolding of platform-based design, I'm not claiming that I solve the world's problem. You have to put components and their mathematical abstraction into that scaffolding to be able to do anything. Now, one thing I would like to stress is requirements. And, I already said at the beginning, but requirement engineering, in my opinion, is the challenge number one today. No matter which method you use to design your system, think about how you're going to formulate, extract, and use requirements. The approaches is for architecture, abstraction, and automation. So design flows, models, and architecture. And of course, design flows, not but platform-based design. Okay. So now, how to deal with the dynamics of this swarm? So how do you design with this swarm? What is the key component to be able to design application with this swarm? So this one is actually the view of Cisco, and so they say that indeed not a operating system as usual. So in some sense, when you think about resources, you think application using resources, that's an operating system. If you really think carefully about what an operating system does for computing, is offering the application program the resources of the computer in an intelligent way, in an automated way. So what we need is an operating system of the planet. It's a planetary operating system. And so in some sense, it's my last slide, the swarm as a platform. So this one is also a big research project we just started about 6 months ago. The head is in Berkeley, but there are 35 different universities connected to us to try to do that in the United States. So you have resources, and resources we have computing, storage, network, actuators, sensors. You got applications, you get home security, emergency, energy efficiency, health monitoring, and all that kind of stuff. And you have to impedance match the two, and that is what we call the Swarm OS. And indeed, what we are focusing on in this Terra Swarm approach is to use well, there was an overlay that has disappeared on me, but this is the way in which you connect the two words is through platform-based design. So the Swarm OS is a way of building that virtual layer that offers the capability of using your resources. And with that, I thank you very much for your attention. Let's go Swarm.